Today we are going to learn how to find the number of possible outcomes of one or more events. First thing that we need to do is get some vocabulary defined. So our first vocabulary word for today is sample space. Sample space is the set of all possible outcomes of one or more events. And you find the sample space with tables and tree diagrams. So use table and tree diagrams to find sample space of two or more events. Our next vocabulary word is fundamental counting principle. It's not really a complicated definition. It will seem complicated until you see it in practice because we're going to use the algebraic form. So get the definition down, and then when you see it in practice, it will make more sense. So the first part of the definition is you have an event, and we're going to call that an event M. But imagine like you're flipping a coin. So that's an event. And it has M possible outcomes. So if you're flipping a coin, it's going to have two possible outcomes. Then the next part of the definition is you have a second event. So the second event, N, has N possible outcomes. Then the fundamental counting principle says the total number of outcomes, and I'm going to abbreviate number with the number sign. If that doesn't make sense to you, write it out. Equals M times N. All right, and if you have more than two events, then this can be expanded to cover more outcomes. And we'll look at that in some of our examples. So that's the definition, and like I say, this will make more sense when we start working some problems. A compound event consists of two or more events. So compound, like think of a compound word. A compound word is like tree house. It has two words and you put it together. So that's the same thing with a compound event. It consists of two or more events. And then the probability of a compound event is the ratio of favorable outcomes to the total possible outcomes. So some of this should start making sense as you put the pieces that we've learned before together with the pieces that we're learning today. So let's look at a few examples. So example 1 says, find a sample space. You randomly choose a crust and style of pizza. Find the sample space. How many different pizzas are possible? So we're only looking at sample space, which is outcomes. We are not looking at probability yet. So kind of get the difference of that in your mind. We're going to do this using a tree diagram. This is not going to be your choice to do every time, but I want you to see how a tree diagram looks. So I'll show you. So pause the video and go ahead and set this up. You have crust, style, and then the outcome. And then I've already gone ahead and written my crust. We have thin crust and stuffed crust. And then the thin crust, if we choose thin, we can choose Hawaiian, and I'll end up probably abbreviating because it gets repetitive. We can choose Mexican. We can choose pepperoni, or we can choose veggie. So then our outcome is thin Hawaiian, or we could choose thin Mexican, or we could choose thin pepperoni, or we could choose thin veggie. Okay, so there's already 4 different kinds of pizzas we can choose. So now let's look at stuffed crust, and it's going to be the same thing. We can choose stuffed Hawaiian. We can choose stuffed Mexican. We can choose stuffed pepperoni, or we can choose stuffed veggie. And then our outcomes are going to be the same thing except stuffed Hawaiian, stuffed Mexican, stuffed pepperoni, or stuffed veggie. So I can count my outcomes. I have, I'll use a different color again, maybe. So I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 outcomes. And a lot of us probably don't necessarily need a tree diagram, but I wanted you to see how it works because it is a good picture, a good illustration of what the outcomes are and how you get those. All right, our on your own problem says, what if the pizza shop adds a deep dish crust? Find the sample space. How many pizzas are possible? All right, so you already have 8 outcomes, so I don't expect you to do that again. But go ahead and do a tree diagram for the last part, the deep dish, and then check your answers. There's what your tree diagram should look like. You have deep dish, and then I didn't go ahead and rewrite the outcomes like I did on the first example. I'm a lazy mathematician. But then you can see you have 9, 10, 11, 12 outcomes. All right, example 2 says find the total number of possible outcomes. Find the total number of possible outcomes of rolling a number cube, it should say cube, and flipping a coin. Use a table to find the sample space. Let H equal heads and T equal tails. Okay, so in this table, my across is what I'm rolling, and then my columns are what I'm flipping. So I can roll a 1 and flip a heads, roll a 1, tails, roll a 2, heads, roll a 2, tails. So I think you start seeing the pattern here. So go ahead and fill out your table. And then we can count these, and there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the number of possible outcomes is 12. All right, method 2 says use the fundamental counting principle, identify the number of possible outcomes of each event. Okay, so event 1 is rolling a number cube. And I have 6 possible outcomes. Then, so this is event 1. Event 2 is flipping a coin. And I have 2 possible outcomes. So the fundamental counting principle says number of possible outcomes from event 1 times number of possible outcomes of event 2. Multiply those together, and I get 2. And you can see that they match. So 2 different ways to solve the problem, got the same answer as I should. Go ahead and do the on your own problem and then come back and check it. All right, so the on your own problem says you have 7 different colored t-shirts, 4 different pairs of jeans, and 3 different pairs of shoes. How many different outfits can you make? So event 1 is the t-shirts, 7. Event 2 is the jeans, 4. Event 3 are shoes. Fundamental counting principle says I multiply each of those events together. So I'm going to do that. 7 times 4 is 28. 28 times 3 is 84 different outfits. And I just want to point out one of the things that I'm doing, notice how I keep my events and then I list them out. It's a small thing that will probably save you some mistakes in the future if you just kind of jot out so you don't lose track of what you're writing down. Example 3 says finding the probability. So now we're looking at probability, not outcomes. Finding the probability of a compound event. In example 2, what is the probability of rolling a number greater than 4 and flipping tails? Okay, so my first event is rolling greater than 4. So I have greater than 4 would be 5 and 6. So I have 2 possible outcomes out of 6 total. Then flipping tails, I have 1 possible outcome out of 2. So I have to treat these kind of as separate things. The fundamental counting principle says multiply them together. 2 times 1 is 2. 6 times 2 is 12. So the probability of the event rolling a greater than 4 and flipping tails is 2 out of 12, which simplifies to 1 out of 6. And then for our non-mathematicians, that would be 16 2/3%. So there is my answer for that. So notice the work that I have to do to find the probability. Example 4 says find the probability of a compound event. You flip 3 nickels. What is the probability of flipping 2 heads and 1 tails? Use a tree diagram. Okay, so I've gone ahead and set this up for a tree diagram. We have event 1. I'm going to flip a nickel, and when I flip a nickel I can get either heads or tails. Then my event 2, if I flip heads event 1, then event 2 I can flip the second coin and I'm going to get heads or tails. Then event 3, I'm going to flip a coin again and I can get heads or tails. If I get tails, I can get heads or tails again. Then I'm going to do the same thing. If I get tails, I'm going to flip the second one. I can get heads or tails. Then I'm going to flip the third nickel. I can get heads or tails. Heads or tails. So my outcomes look like this. And I'm just going to kind of go straight across. I could have heads, heads, heads. I could have heads, heads, tails. I could have heads, tails, heads. And I could have heads, tails, tails. Okay, then for the second part, I could have tail, heads, heads. Tail, heads, tails. Tails, tails, heads, tails, and then 3 tails. So notice how I'll just kind of circle what I've done so you can see it. So like for my first one, I read it that way. And then, so you just kind of keep going until you get your outcomes. Okay, so then it wants to know the probability of flipping 2 heads and 1 tails. So here would be 2 heads and 1 tails, 2 heads and 1 tails, 2 heads and 1 tails. And that looks like that's it. So my favorable outcomes are 3 out of 1, 2, 3, 4, 5, 6, 7, 8 possible. So the probability is 3 out of 8, which is the same thing as 37.5%. Okay, so that's one way to do it, is a tree diagram. Okay, so on your own, it says in example 2, what is the probability of rolling at most 4 and flipping heads? So how I've set mine up is the first column right here is my favorable outcomes, and my second column is my total possible outcomes. Fundamental counting principle says to multiply, so the probability of this event is 4 times 1 is 4, 6 times 2 is 12. 4 twelfths, which simplifies to 1/3, which is 33 1/3%. Okay, so I just wanted to kind of see how to do that. Go ahead and work through the next examples, and then you can come back and check your work. In example 4, what is the probability of flipping at least 2 tails? I just went back to the tree diagram and I counted. There was 4 possible outcomes out of 8 total, which is 1/2, which is 50%. You rolled 2 number cubes. What is the probability of rolling double 3s? So my first event is to roll a 3. I have a 1 chance out of 6 possible outcomes. Then for the second event, I have a 1 chance out of 6 possible outcomes. Multiply 1 times 1, that's 1 out of 36, or 2 7/9%. All right, then our last on your own problem says, what is the probability of choosing a stuffed crust Hawaiian pizza? So the probability of stuffed Hawaiian is 1 out of 8, which is 12.5%. If you have questions after watching this lesson, please come see me so I can help you work out anything that you don't understand.